Most of the time, when we think about an acid and base reacting, we think of a neutralization reaction. Acids neutralize bases, bases neutralize acids, and that's most commonly written in a double replacement, where I have something starting with hydrogen as my acid, something ending with hydroxide as my base, and then they swap partners so the hydrogen ion and the hydroxide ion come together to make water. The other cation and anion also come together and they make an ionic compound. In most circumstances, the net ionic for that equation is that the hydrogen and hydroxide ions combine to make water. Because water is a liquid, we write that together, and we could think of that as, or the proof or the support that it's one way or that it stays together by recognizing this is the opposite of the reaction for Kw, where water turns into its ions with a very small value for K. So when the ions turn back into water, it has that very large value of K. Some acids and bases may also have ions that form a precipitate. So we want to pay attention to our solubility rules and the observations that we see either in the lab or described to us, because we can have that happen as well. But anytime our acid and base are making a water, it is a one-way reaction or it goes to completion. For strong, as it says, they're going to be ionized at the beginning, and then water would be our only product. The difference when it is weak is not that it becomes a two-way reaction, but in what our products and our reactants are. Even when they are weak, when reacting with one another, when something with hydrogen reacts with something with hydroxide, it makes H2O. The production of H2O from acids and bases is a one-way reaction or goes very close to completion. We could combine Ks for the different processes, but we'd always see a very large K for that. The difference is how we write our reactants. Our reactants might be weak, and when they are, we don't show them as ionized. So HCl would look like this, not including the Cl, but something like HF or HC2H3O2, acetic acid, would be written all together. As a result, we would need that anion in our products. So the anion does appear in our product. And what's important here is we still call this a neutralization reaction, but it's not necessarily totally neutral. Because remember, if I have a weak acid, the conjugate base that I produce is weak. So this is the reaction. This is our neutralization. It's still one way. But after we recognize that I have a weak base floating around in my water, I could see and understand, predict, and or explain why the pH might not be 7 or why our products might not be totally neutral. That's a big key, understanding how the conjugate base and the weak acid act in different ways, whether that's an equilibrium and a K value, whether that's writing a reaction, whether that's looking in a neutralization or titration reaction. So the key here is two separate things. We have a one-way reaction for the neutralization. That'll end up in math, that's stoichiometry, which we'll see. But then we end up with components that are still weak, meaning that they still have some equilibrium involved.